Okay, so let's take a moment to once again recap memory mapped IO and go a little bit deeper into it. As I said, we have a CPU, we have various peripherals, we could also have memory, right, and each peripheral would be given some kind of an address that it is associated with it, right. And when I say something like peripheral A at this address 0x400 and so on, what I mean is that addresses that start from this and go up to some width, right. So, it could be, it may not be just this one address alone, it might be this address, the next address, the next address, next few addresses in series, right. How many? Up to the designer, right. All of those correspond to peripheral A. Now, what that means is, ideally I do not want peripheral A to have to know that it is at this address 0x4000. Why? Because after all, when I am designing a counter, I do not know in which CPU it is going to be used, right. I do not know how many counters are going to be used in the CPU, I might want to use more than one. So, if I try and hard code this address and say, oh, it is a counter, it has to be at this address, that causes problems. Maybe somebody else also designed some other peripheral and they gave it the same address, then what do? I have to go in and change the RTL code corresponding to each of them if I want to do that. Instead of that, what I do is I use something called an interconnect. So, what the interconnect does is something called partial decoding. It basically takes the first chunk of the address out. So, maybe it might take the first 16 bits or it might take the first 24 bits, right. So that there is some small set of bits that are left behind which are sent into the peripheral. But as far as the peripheral is concerned, let us say I put in only the last 8 bits, right. It has 256 addresses associated with it. The remaining 24 bits were decoded over here, which means that I could take the same counter and put one at this address 4000 and the other one as 4001, and the CPU would be able to talk to each one by giving the appropriate address. The counters by themselves do not know at which address they are. The AXI interconnect, this block out here, should know where they are, right. And this part is where things get a little bit tricky, because ultimately we have to sort of watch out for that, right. I mean, how do I get all of this information to my system, right, because of course if I am writing a program and I know exactly where each of these things is and I have constructed this AXI interconnect in a certain way, yes, I can go and write custom software in a certain way which has all of these numbers hard coded into it. But that is where the beauty of the operating system kernel and the device tree and other aspects come into play, because they allow me a cleaner way by which I can specify what kind of peripherals are connected in different places. But I am getting ahead of myself, right. This is stuff that we will be covering in later sessions. Now, the important part is that the CPU by itself just uses the load store operations in order to access the different MMIO address ranges. Now, of course, what that means is that I am assuming that my CPU has some kind of load store functionality, which most CPUs will have. They need some way by which they can communicate with memory, and that is all. All that I am saying is, if it can talk to memory, it can talk through this kind of an interface. There are other kinds of CPUs which have, for example, custom IO logic and different instructions whose only purpose is to talk to IO peripherals. There is in fact a separate IO bus in some CPUs, right. But over time people have sort of come to the thing that at least for generic systems on chip, it is more efficient and a cleaner design to just let everything go through MMIO. Okay, so this is sort of probably the most popular mechanism that exists right now for addressing different kinds of peripherals. Now, as I said, this interconnect plays a fairly important role here, right. It routes the transactions, right, whatever this read write operations are trying to happen from the CPU to whichever peripheral is actually supposed to respond to it. And each peripheral in turn will expose a small register bank, a set of registers that you can read from the CPU or write from the CPU, and this is what we will be taking up as an example and sort of walking through it. So, just to sort of why are we using this whole idea of MMIO? Memory and MMIO, the way that they are accessed from the CPU is the same. But what happens when I access memory or MMIO can have different side effects, right. As far as memory is concerned, in general, if I am just reading from a given location in memory, I expect to get the same data back always. But MMIO could be different. For all you know, you might even implement MMIO from a random number generator, which means that every time you read from it, you get a different value back. Okay. Now, for the purposes of at least the initial parts of this course, I will be assuming a simple 32-bit data width, right, just to sort of keep things simple. But once again, that's a choice. You could have a processor with a different bus width, right, your data bus could be different, your address bus could be different, the registers that you use internally could be different. Primarily what you do is you try and have it such that your data bus, the width of the data bus matches with the size of the registers that you have inside your register file, because otherwise it's pointless. You can't really load in a value and sort of fill up a register with it, right. But as I said, these are choices. 32 bits is a nice sort of useful size which allows a large amount of different kinds of computations. Nowadays a lot of processors are 64-bit processors. The fundamental concepts don't change, so I will be using this for explaining most of the ideas over here. Now, there is also this notion of a cache. This is something which I am just mentioning for the sake of completeness. It is not something that I am going to get into in any detail as far as this course is concerned. The computer organization course would give you a bit more of a flavor for what caches are and so on, but ultimately this is a performance related optimization, right. And the reason why caches are used in the first place is because memory, external memory blocks can be slow, and by slow what I mean is potentially because of the large size, the large amount of data that needs to be there, stored there and so on, the time required to read or write data from a given location in memory could be hundreds of CPU clock cycles. To speed things up, what we do is we bring in smaller but faster memory blocks that are closer to the CPU and call them cache memory. What we mean by cache spelled as C-A-C-H-E, right. So, the cache memory, the idea behind cache memory is it's a temporary storage which sort of keeps track of what is there in the main memory, but if the CPU needs to repeatedly access the same data, it will be able to get it very quickly from the cache, right. Now, details of these cache architectures are out of scope. The only thing that we really want to mention at this point is, in case you come across these terms, L1 cache is usually the level 1 called the fastest cache that is present in the system. It's close to the CPU, it's also very small in size. L2 is the next level, L3 is one further out, and all of these in turn are faster than the main memory of the system. If they are not, then it really does not make sense to have a particular level in the cache, and you might just want to take it out instead, right. Now, as far as MMIO is concerned, why is this important? There are two aspects that come in over here that I have mentioned. One of them is, as I told you, memory mapped IO means that I am not just taking data from a particular location in memory. I might, for example, be reading data back from a sensor or an A to D, right, analog to digital converter, or a random number generator or something else of that sort. And the most important point to note over there is, every time I read a value back, I could potentially get a different result. Unlike memory, where the idea is every time I read it, I get back the same data. Now, as the whole point of a cache memory is that I am assuming that every time I read from memory, I am getting back the same data. Therefore, I can put it in the cache and I can read it back faster, right. But we also need to keep in mind that if I am reading from a sensor, I do not want it to be cached, because if I just keep getting back the same data every time I read, it is defeating the purpose of having the sensor. So, typically MMIO has to be uncached. There are different ways of doing this. Sometimes we will be able to specify that entire sort of address segments in the bus should not go into the cache, right. The others are that we can actually have a software control which says addresses in this range should not be cached. So, there are some, obviously there has to be some way by which I can inform the underlying hardware as well as software how to behave. There is also this notion of ordering, which says that in general when I am writing a program, let's say in C, if I have two load instructions, it may not matter in which order I perform them, right. Let us say I have a load from location number 1 and load from location number 2, they are going into two different registers. It generally speaking does not matter in which order I perform the loads, and the buses sometimes take advantage of this and reorder the memories, reorder the load instructions. Similarly, they may also reorder store instructions, provided that there is no chance of a conflict or of something changing the behavior, underlying behavior. Now with MMIO, the story is slightly different. In general, you do not know what kind of action is happening as a result of the load, and therefore the typical preferred behavior is to have it strongly ordered, meaning that if there are two instructions in your assembly language or your machine code, they have to be executed in the same order. Okay. So these are things that become important when we look at it from the point of view of how MMIO gets implemented in practice. It is just worth mentioning now because they will be something that comes up later as well when we are writing code.